All that remained was to build one of the world's largest enclosed spaces for the new terminal.
A breeze, except by now, the clock was ticking. Hong Kong was due to be handed back to China by the British government. The project had to be completed before the handover, giving the engineers just 3 years to build one of the world's biggest airports. But the fast-approaching deadline wasn't the engineers' only problem.
Here in Hong Kong, the designers were aiming to be very big. They wanted to create one of the biggest enclosed spaces in the world, and they wanted it to be light and airy.
A big space requires a big roof. At 700 meters wide and over a kilometer long, this was no ordinary roof. The airport architects insisted on a jaw-dropping design mirroring the rolling waves of the South China Sea. It was an engineer's nightmare. A roof this size would need lots of muscular columns to take its weight. But the architects didn't want heavyweight structures cluttering up their light, spacious terminal.
This is a huge space with almost nothing to stop passengers moving around freely. This is one of the pillars holding up the roof. The next one is all the way over there. And in the other direction, it's all the way over there. Those are huge spans.
So how do such a small number of thin columns support a big roof? The answer? Make the roof really light. And the trouble is, a light roof isn't usually strong. Funnily enough, making something light and strong is what plane designers have to do all the time.
For the solution, the designers looked to the heavens and found inspiration in a World War II bomber.
It's the Wellington, a twin-engine British bomber used for nighttime raids over Germany in the Second World War. The crucial thing about the airframe was its strength. British engineer Barnes Wallis had found a revolutionary way of making a frame light and strong. It looks more holes than metal, and the secret was in the way he arranged the material. It's not about the amount of metal you use, but how you use it. I've devised an experiment at my workshop to show how, with steel, less can be more.
Okay, if we're ready, let's try and get it down, but let's get it between the bars.
I don't get just anyone to be my technical advisor. Martin Manning was the chief structural engineer at Hong Kong International Airport.
Okay, can we get down?
First, we're going to load up a standard I-beam used in buildings all over the world, with 2.5 ton in weight, about the same as 2 family cars.
So, here we go.
As the chain slackens, the beam takes the full load.
You can see it bending now.
Yes, I can see it bending.
This 130 kilo beam is holding up. Just. What happens when we increase the weight to 3.5 tons?
Oh, here we go.
So, let's slacken her off and have a look.
Take the load off the crane.
So when the chains start to go slack...
There she goes.
My word, that is not liking it at all.
Don't take it any further.
That's failed, isn't it? That's broken.
That is seriously broken.
That never even got near it.
The steel beam fails completely at 3.5 tons. You could give this beam more muscle by bulking up, but that would also make it heavier, and they didn't want that at Hong Kong. Amazingly, we can send the I-beam on a diet and still make it stronger. Think Wellington bomber. The answer lies in simple geometry.
So there are things you can do with just the same amount of material, the same weight, but organised in a different way, in a different shape, a different form.
Absolutely.
And that's what we're going to do next.
Yep.
We better tidy this up. That beam's really ruined.
Broken.
Spoiled.
We're in trouble now.
Taking a cue from Barnes Wallace's Wellington design, I've reorganised the steel into a series of triangles. This lattice beam weighs almost 20 kilos less than the I-beam, yet it should be stronger if the maths is right. The load is spread through the lattice, so it won't bend, or so Martin tells me.
And you think this will be stronger? Yeah. Just because of the shape, the arrangement?
I'm going to test Martin's confidence and load it with a much heavier weight.
Right, let's have the lot on. All of it.
We're loading up every slab we can find. That's 4.5 tons, a ton more than the I-beam could hold.
All the way back.
Remember, this lattice weighs less than the I-beam.
Okay, settling.
It's down.
So, watch it slacken off. Now, at this point, the I-beam just folded. Look at that.
That's not moved at all. There we are.
No.
That's 4 tons of concrete and half ton of steel.
And that's now happily supporting, what, 4.5 tons? And it's not even... that's content.
Yeah, that's quite content. The other one easily failed at 3.5, so say it was safe at 2.75, so it's nearly twice the load.
And it couldn't be any clearer, could it?
So that shows how you arrange the steel makes a huge difference to the strength. Our lattice was composed of very strong triangles, just like the Wellington bomber. And the curved lattice of steel, also made of triangles, was exactly what the engineers needed to span the terminal roof in Hong Kong. Each 36-metre span could be bridged with just one huge but light lattice structure.
But it supports itself without the need for hefty pillars getting in the way, leaving the space free for passengers like me to roam around.